Today, I'll be presenting my dissertation, which is titled Towards a Fall-Tolerant Framework for Bipedal Robots. Cool. So due to their form, bipedal robots have the unique capability to navigate diverse terrains, from unstructured environments to human-centric environments, as you can see, as demonstrated by Cassie and Baymax on the screen. Furthermore, exoskeletons such as A Fall-Tolerant can act in parallel with the user's limb and restore mobility. Therefore, bipedal robots are the ideal candidates to assist us in day-to-day tasks, as well as critical tasks. However, despite their unique capabilities, the real-world deployment of bipedal robots is limited. Their limited deployment can be attributed to various factors, such as their highly dimensional, hybrid, and at times highly constrained nature, which makes it challenging to achieve a stable motion, especially in the face of disturbances and uncertainties. These disturbances and uncertainties can lead to a fault, which can then lead to a fall, as demonstrated by Cassie and Marla on the screen. Falls are undesirable because A, they can prevent the robot from completing its task, they can result in irreparable damage to the surrounding area, and they can also lead to operator and bystander injuries. And while a well-designed controller can actually counteract the effects of these disturbances and uncertainties, the infeasibility for accounting for all the potential disturbances and uncertainties that may be encountered during real-world operation still makes falls inevitable. Therefore, it's not only important to implement robust control algorithms, but also to implement reliable fall prediction algorithms. A way to do this is through the Fall-Tolerant Framework, whose objective is to enhance the robot's ability to navigate unstructured environments by equipping it with capabilities to assess, adapt, and respond effectively to uncertainties and disturbances. This framework achieves this through a combination of various algorithms, such as a robust controller, a fall prediction algorithm, or a recovery algorithm, and so on and so forth. My research objective has therefore been to contribute to the implementation of a fall-tolerant framework for bipedal robots by developing robust controllers and reliable fall prediction algorithms. As such, today I will be presenting my contributions through two projects. The first project is on robust, comfortable sit-to-stand motions for the fully actuated lower limb exoskeleton A Fall-Tolerant that is designed by Wondercraft. This project contributes directly to the robust controller part in the Fall-Tolerant Framework. In comparison to literature, the contributions of this project are as follows. We modeled the sit-to-stand motion using the full 3D exosystem, whereas in literature, only the sagittal plane portion for the sit-to-stand motion is captured, which then makes it difficult to ensure that the hardware constraints are met in the other planes of motion. Secondly, an analysis of two dynamic sit-to-stand motions, which we term chair-to-stand and chair-to-crouch-to-stand. And as you will soon see once we delve into this project, each of these motions is ideal for certain perturbations. When we look at literature, the motions that are generated are only for simplified models of the exosystem, and they mostly match only the chair-to-stand motion. Next, a novel and systematic way of choosing the control objectives for highly constrained systems such that they are independent of the contact constraints. To the best of my knowledge, no such systematic way exists in literature. And last, physically motivated robustness tests that do cover the user and their affordances. And because of this, the results of these tests can then be utilized to inform new hardware design or to further robustify the controller. Here are the related publications for this project, or you can scan the QR code if you do so wish. See somebody trying to scan. Okay. The next project is on developing reliable fall prediction algorithms for bipedal robots. This is a project that utilized two different robots, a planar four-link robot that is based off of the A Fall-Tolerant exoskeleton, and the digit bipedal robot that is designed by Agility Robotics. As the name implies, this is a project that contributes directly to the fall prediction algorithm part in a fall-tolerant framework. In comparison to literature, the contributions of this project are as follows. In this project, we are capable of detecting falls arising from multiple faults, whereas in literature, they only detect faults that only arise from one type of fault. Secondly, our algorithms are capable of estimating the time left to recover. To the best of my knowledge, no such method exists in literature. And lastly, we have an open source data set of a full-size 3D robot that's comprised of both simulation and hardware trajectories with various faults. Again, to the best of my knowledge, no such data set exists in literature. In terms of each of the individual robots, the contributions are as follows. For the planar 4-link robot, a multi-classification-based algorithm that is capable of detecting multiple faults while providing sufficient time for corrective motions to be taken, as well as a comparison of physics-based and data-based algorithms. For the digit robot, a 1D CNN-based algorithm that is capable of detecting multiple faults and predicting the time left for corrective motions, both offline and online in simulation as well as in hardware. And lastly, the open source data set that is comprised of simulation and hardware trajectories for the digit bipedal robot. Here are the related publications for this work. And now I'd like to get started with the Sit-to-Stand project. Some background information before we get started. A bipedal robot navigating about the world, such as the robot turning on the screen, can be described as a hybrid system. A hybrid system consists of both continuous and discrete states, which are also known as domains. The continuous dynamics of a robot evolve in each domain. For example, for the turning robot on the screen, it has 3 domains: a right stance domain, a double support domain, and a left stance domain. The transitions between domains happen either when the continuous dynamics in the domain are no longer valid or as a design choice for simplicity. For example, for the robot on the screen, if we assume that the double support domain is instantaneous, the transition from the right stance domain to the left stance domain happens when the right stance foot breaks contact with the ground and the left swing foot gains contact with the ground. Next, the continuous dynamics of a bipedal robot can be represented using the floating-based dynamic equation shown on the screen, which is derived using the Lagrangian method. This equation consists of an inertia matrix, a Coriolis matrix, a gravitational vector, a torque distribution matrix, a Jacobian that maps your contact wrench's gamma to your generalized coordinates q, and finally, your control input. This equation has 2 unknowns, your generalized coordinates q and your contact wrench's gamma. Therefore, we need a second equation in order to solve for these unknowns. The second equation takes the form of the contact constraint, and this equation essentially ensures that the contacts that the robot makes with its environment are respected. Let's now delve into how we achieved these robust, comfortable sit-to-stand motions. Why sit-to-stand? Well, as the Rex exoskeleton is demonstrating on the screen, we care about sit-to-stand because it is necessary for the unassisted transition to the exoskeleton and is therefore a precursor to walking and other locomotion. This project utilized the Atelant exoskeleton, which again is a fully actuated hands-free lower limb exoskeleton that was developed by Wondercraft for people with paraplegia, that is, people who are paralyzed from the waist down. Atelant has an onboard computer and batteries, and has an IMU on the torso. It has 12 actuated joints, and its user's range is as follows: 5'1" to 6'3", and 110 to 194 pounds, which meant that I barely made the cutoff for using Atelant, but I did. Our objective for this project was to achieve a safe, comfortable, assisted sit-to-stand motion for the exoskeleton plus user system, all while respecting the hardware bounds and being robust to changes in the user characteristics, such as having different users in the exoskeleton, and the user's environment, such as having different chair heights. Here, we define comfort in terms of user force and torso pitch acceleration. As demonstrated by my brother Solomon on the screen, there are various ways that one can stand up. For example, the way you stand when you have a heavy backpack strapped on is different from the way you would stand without the backpack. Therefore, we decided to develop 2 dynamic sit-to-stand motions using hybrid system: the chair-to-stand motion and the chair-to-crouch-to-stand motion. The chair-to-stand motion consists of 2 domains, the sitting domain and the standing domain, whereas the chair-to-crouch-to-stand motion consists of 3 domains. The sitting domain, the standing shift domain, and the standing extend domain. Given that the exoskeleton is in contact with the chair during the sitting domain, it has 3 contact points, the chair and the feet. In the other domains, the exoskeleton only has 2 contact points, the feet, given that it is no longer in contact with the chair. The difference between these 2 motions is as follows. For the chair to stand motion, the center of mass is shifted forward and the joints are simultaneously extended, whereas in the chair to crouch to stand motion, the center of mass is first shifted forward and the joints later extended. Furthermore, the chair to stand motion is constrained to be symmetric along the sagittal plane. In other words, the left and right hand sides of the exoskeleton are constrained to mirror each other, whereas the chair to crouch to stand motion is allowed to be asymmetric. The continuous dynamics for each of the domains are derived using the floating-based Lagrangian model that we went over in the background. Note the 2 additional terms that pop up here due to user force. The open source package Frost that is designed by Professor Yanga-Herod was utilized to generate the 2 trajectories for the sit-to-stand motions. Due to the highly constrained nature of the equations of motion for the sit-to-stand task, we decided to design our control objectives such that they are well-defined and independent to the desired contact constraints. We do this so that the controller is not actively fighting against the contact constraints and such that there exist control inputs that allow the robot to achieve its desired task. To find these control objectives, we use the contact interaction matrix on the screen, as well as optimization. In the next few slides, I will briefly go over the derivation of this matrix. Given your tracking error, which is defined as the difference between your actual parameter and the desired evolution of those parameters, our control objective is to drive the tracking error terms to 0. If the desired evolution of our parameters HD is twice differentiable, we can then define the double derivative of our tracking error as follows, where JH is the partial derivative of our actual parameters H0 with respect to our generalized coordinates Q. In other words, JH is the Jacobian of H0. Now, given the dynamic equations, the control objective equation, and setting the double derivative error to the following equation, our equations of motions can now be written as follows, where I is the contact interaction matrix, and it captures the interaction of the contact wrenches and the motor torques in achieving the contact constraints and control objectives. The top row of this matrix is fixed by the dynamic equation, whereas the second row depends on the Jacobian of the control objective function H0. Given this, in order to design our control objectives, we implement an optimization to find H0 such that its Jacobians approximately satisfy 2 equations related to the second row of the contact interaction matrix. The first equation ensures that the control objectives are in the null space of the contact constraints. When this equation is satisfied, the controller does not act in the directions of the contact conditions. The second equation ensures that there exists a U such that our equations of motions are satisfied. This is because M is not necessarily a square matrix, and it might actually be rank deficient. In order to implement the trajectories that were found with trajectory optimization using Frost, as well as our control objectives, we designed a quadratic programming-based input-output linearization controller. This controller minimizes the error between the nominal and applied motor torques and the nominal and applied user force. Additionally, it enforces the equations of motions, as well as feasibility constraints, such as constraining the 0 moment point to be inside the support polygon. The resulting closed-loop motions are shown in the videos, and as you can see, the chair-to-stand motion respects the left-to-right symmetry, whereas the chair-to-crouch-to-stand motion is asymmetric and takes longer than the chair-to-stand motion. Despite these differences, both of these motions require relatively low user force, as well as torso pitch acceleration. And because of that, we can conclude that both of these motions should be relatively comfortable for the user. To analyze the range of operability of the 2 closed-loop sit-to-stand motions, we decide to employ the use of physically motivated robustness tests. We do this because the highly nonlinear nature of our problem made it infeasible to analytically implement stability methods. In the robustness tests, we subjected our controller to the following perturbations. different users in the exoskeleton, different chair heights, zero user force, spasticity in the knee joints, and asymmetric motor torque controls. Our criteria of success was as follows: tracking in steady state air, torso pitch acceleration, user force expected by the controller, ZMP and friction constraint violation, and finally, joint and motor torque limits. From these physically motivated robustness tests, we found out the following. Both motions handle various users in the exoskeleton well. The chair to stand motion is better at handling changes in chair height, that it's possible to achieve unassisted sit to stand motions, and finally, that the chair to crouch to stand motion is better at rejecting perturbations that result in asymmetry. To further assess the effectiveness of our control objective as well as our controller, we compare them to related work in literature. Note that the control objectives in literature consist of a combination of the center of mass and the joint angles of the exoskeletons, and the controllers that are utilized have a similar objective function to our controller, but they don't enforce all the feasibility constraints that our controller does. From this comparison, we found out the following. Our control objectives are better at respecting contact constraints, and they actually result in lower torso pitch acceleration. And finally, our controller was able to reject more perturbations. Our analysis so far has been done on closed-loop motions that were derived in the Frost simulator, which does not take contact dynamics into account and therefore does not simulate real-world conditions. Recall that Frost is the open source package that was utilized to generate the two trajectories for the two sit-to-stand motions. Therefore, in order to emulate the real-world conditions that the exoskeleton would operate in, we decided to continue our analysis with two simulators that do take into account contact dynamics, Jiminy as well as MuJoCo. This is work that was done in collaboration with Professor Ayanga Herod and his student Victor Paredes at The Ohio State University. And the preliminary closed-loop motion of the chair to stand trajectory with the MuJoCo simulator is shown on the screen. Unfortunately, due to Attenlant breaking, we were unable to do hardware tests. For more information, as well as to see the results with the Jiminy simulator, please see Chapter 4 of the dissertation. In summary, this project contributed to the implementation of robust controllers by introducing a systematic way of choosing control objectives. To analyze the range of operability of the resulting two closed-loop sit-to-stand motions, we used physically motivated robustness tests. To assess the effectiveness of the proposed control objectives and controller, we compared them to related work in literature, and we found that our control objectives were better at respecting contact constraints and that they resulted in motions that required lower torso pitch acceleration. We also found that our controller was better at rejecting perturbations. Lastly, in order to emulate real-world conditions, we implemented the sit-to-stand motions in two simulators that do take into account contact dynamics. The future work for this project is as follows: an extension to other robotic platforms, as well as to other motions, and implementation on hardware if Attenlant cooperates with us. I'd now like to move on to the fall prediction project. Some background information. Falls are caused by faults, which are defined as unforeseen deviations in one or more operational variables. In terms of their time dependency, faults can be categorized into three different categories: abrupt faults, which are step-like or rapidly varying; incipient faults, which evolve gradually over time; and lastly, intermittent faults, which are sporadic or non-continuous. The states of a robot can in general be divided into three classes: safe, falling, and fallen. The safe class can be categorized as normal, and the falling and falling class can also be categorized as faulty. And lastly, as discussed by the authors in 1, individual stability metrics could be a necessary but not sufficient condition to predict falls. Let's now delve into the design of a reliable fall prediction algorithm for bipedal robots. The objective of a fall prediction algorithm is to reliably detect critical faults with sufficient lead time to deploy a recovery strategy. Critical faults are defined as faults that lead to a fall. Lead time is defined as the time to react, and it is defined as the difference between the time of the actual fall and the predicted fall. Note that literature suggests a minimum lead time of about 0.2 seconds, and here reliability is determined using false positive rates and false negative rates. Our objective is as follows. For the bipedal robot digit, we would like to detect all critical faults, maximize lead time while minimizing false positive rates, and lastly, accurately estimate lead time. The challenges that are associated with this objective are as follows. The crowding phenomenon caused by incipient faults. This is the similarity between the normal and faulty data, which makes it difficult to separate the normal data from the faulty data. The masking effects of the controller as it tries to mitigate the effects of the fault. The direct relationship between false positive rate and lead time. In other words, maximizing lead time can actually lead to high false positive rates. The sporadic nature of intermittent faults. And lastly, the diminishing number of data points with increasing lead time. Given all of these challenges, we decided to start our investigation by developing a fall prediction algorithm for the task of standing with a planar 4-link robot. We do this as a way of simplifying the problem, all while providing a means to scale up to more complex robots such as digit and more dynamic motion such as walking. The problem statement for the planar 4-link robot is as follows. Given an upper bound on false positive rate and false negative rate, we aim to develop a fall prediction algorithm for the task of standing that detects all critical faults while maximizing the lead time. Here, a fall is defined as any link other than the feet coming in contact with the ground or the feet being off the ground, and critical faults are emulated by applying forces to the torso. We solve this problem statement in 2 steps. The first is the detection of critical, abrupt, and incipient faults, and the second is the detection of all 3 critical faults. To detect critical, abrupt, and incipient faults, we propose 2 binary classification algorithms, the SVM-based binary classifier and the nearest neighbor-based binary classifier. The SVM classifier utilizes the SVM implementation from scikit, and it is trained on safe and faulty data, whereas the nearest neighbor classifier utilizes the word minimum variance and Euclidean distance methods, and it's trained only on safe data. Both of these classifiers make use of sliding windows. The features for the classifiers were chosen as follows. These features were chosen based on their correlation with lead time, as well as other features commonly used in literature. To analyze the performance of these 2 binary classifiers, we train the algorithms and evaluate them on testing data across 5 folds. Note that the desired false positive and false negative rates are set to 0, and that all the results that I will be showing from here on out will be with false negative and false positive rates of 0. We start our evaluation using just abrupt trajectories and just incipient trajectories. And as you can see, both of these algorithms achieve similar results. However, when trained and tested on both abrupt and incipient faults, the SVM algorithm outperforms the nearest neighbor algorithm. Despite this, given that both of these algorithms achieved lead time greater than 0.2 seconds, we can conclude the following. That both algorithms are a viable option for fall prediction arising from critical, incipient, and abrupt faults, and that the nearest neighbor classification algorithm should be used when faulty data is sparse. And with that, we have successfully implemented the first step of our problem statement, and we now progress to the second step. For the detection of all 3 critical faults, we decided to forego the use of both binary classifiers. And the reason we do this is because even though the SVM algorithm performs better than the nearest neighbor algorithm when trained and tested on both faults together, its resulting lead time when trained on both faults together is less than its average when trained on the faults separately. A similar phenomenon is observed for the nearest neighbor algorithm. As a result, we now propose the use of an SVM multi-classification algorithm for the identification of all 3 critical faults. This proposed algorithm is comprised of 3 binary classifiers that are run simultaneously, an SVM fault identifier for identifying the types of faults in a window, Note that this identifier has a delay of about 0.07 seconds, an incipient fault detector for detecting incipient faults, and an abrupt fault detector for detecting abrupt faults. Note that the output of the abrupt fault detector is only utilized when the SVM fault identifier identifies an abrupt fault. With the proposed multi-classification algorithm, the difference in lead time when trained on both faults together versus separately is reduced from 0.08 seconds to 0.03 seconds. And now I know that this difference of 0.05 seconds does not seem to be a big deal, but we can answer that during the questions time as to why this was important. Now, given that intermittent faults are comprised of abrupt and incipient faults, this proposed algorithm is actually able to detect critical intermittent faults with an average lead time of 0.82 seconds. And with that, we have fully solved our problem statement for the planar four-link robot, and we can now progress the development of a fault prediction algorithm for the bipedal robot Digit during the task of standing. I was assisted on this project by Gokul over there, who is a master's student of Michigan. Our objective now is to detect all critical faults, maximize lead time while minimizing false positive rates, and accurately estimate lead time for the task of standing in hardware as well as simulation for the bipedal robot Digit. We now define a fall when the center of mass is below a specified threshold. And similar to the planar four-link robot, critical faults are still emulated by applying forces to the torso. Given that the resulting lead time and false positive rates for the SVM multi-classification algorithm are greatly impacted by user-selected features, and also given the fact that extracting these features for complicated bipedal robots like Digit is non-trivial, we decide to utilize a 1D CNN-based algorithm for the fault prediction of Digit. We specifically choose a 1D CNN due to its equivariance to translation, as well as due to its ability to recognize local patterns when processing data with a grid-like topology. Note that the trajectory of a bipedal robot can be retrieved by a 1D grid taking samples at fixed time. The proposed 1D CNN-based fall prediction algorithm detects all three critical faults while maximizing lead time, minimizing false positive rates, as well as predicting lead time. This algorithm is comprised of three components: a critical fault classifier for identifying fault-related faults, or in other words, critical faults, a lead time classifier, which categorizes windows containing critical faults into three distinct ranges, as shown, and a lead time regressor, which predicts lead time for windows with critical faults and lead times in the range of 0 to 1 second. The features chosen for each of the three components are a combination of stability metrics as well as other terms. And in order to validate our presented methodology, we introduced a new data set. This data set includes both simulated trials and hardware tests for the bipedal robot Digit. And you can access this data set on our lab's website by scanning the QR code on the screen, which will also pop out on the other slide. In order to prevent the robot from sustaining damage during hardware data collection, we did not allow the robot to fall to the ground. Therefore, the true lead time isn't known for hardware data. Instead, we use response time, which is the time to detect, and it's defined as the difference in time between the detection of the critical fault and its introduction. Note that response time is undefined for intermittent faults, given the fact that they're comprised of multiple faults. We now define a fault when the center of mass is below 0.12 meters for simulation and 0.95 meters for hardware, because again, the robot was not allowed to fall all the way for hardware. We will now evaluate the performance of the individual components of the proposed algorithm when trained on abrupt and incipient simulation data and evaluated offline on various faults in hardware as well as simulation. We start with a critical fault classifier. And as you can see, the critical fault classifier is successful at detecting all three critical faults both in hardware and simulation, with lead times way greater than 0.2 seconds and with 0 false positive rate. The difference in response time that you can see between hardware and simulation data can be attributed to the lower force profiles that were applied in hardware. In fact, when we applied these same lower force profiles in simulation, the simulation data resulted in the same behavior that we observed in hardware. Given that the true lead time is unknown for hardware data, we assess the effectiveness of the lead time classifier using just simulation data. And as you can see, the lead time classifier achieves an accuracy greater than 95% for lead times less than 2 seconds and an accuracy of 80% for lead times greater than 2 seconds. This decrease in accuracy for lead times greater than 2 seconds can be attributed to the diminishing number of data points with respect to lead time. Similar to the lead time classifier, we assess the performance of the lead time regressor using only simulation data. And upon evaluation, we found out that the maximum difference between the predicted and the actual lead time is only 0.09 seconds. Given our algorithm's successful performance offline, we decided to test its performance online. So we will now evaluate the performance of the proposed algorithm when run online for individual trajectories in both hardware and simulation. To demonstrate the effectiveness of the fall prediction algorithm when run online, we will showcase the digit robot falling when a fall is predicted, but a recovery controller is not activated. Note that given the fact that implementing a recovery controller was outside the scope of this work, we use Agility Robotics base controller as the recovery controller. For all the videos that will be shown in this section, the switch from the nominal standing controller to the recovery controller will be visualized by a green circle appearing around digit in the highlighted video. Again, note that this switch will be determined by our fall prediction algorithm. The other video will showcase the digit robot falling when the switch is not made, and the time of the simulation will be shown here. We will start with an abrupt fault that is with a critical abrupt fault, that is applied at 30 seconds. And as you will soon see, if the controller is not switched when our fall prediction algorithm predicts the critical fault, the robot falls. That will play again. A similar phenomenon is observed for a critical incipient fault applied at 20 seconds. And we can see that again. Next, we will take a look at the algorithm's performance on intermittent faults that are comprised of 2 faults. In the next few slides, we will again see the digit robot falling when a fall is predicted by the algorithm, but a recovery controller is not activated. We start with an intermittent fault comprised of 2 abrupt faults. Next, an intermittent fault comprised of an abrupt fault followed by an incipient fault. Next, an intermittent fault comprised of an incipient fault, which is then followed now by an abrupt fault. And lastly, an intermittent fault that's comprised of 2 incipient faults. For hardware tests, we demonstrate the effectiveness of this algorithm by showcasing its ability to detect all 3 critical faults. Note that due to the complexity of replicating the same fault twice in hardware, we will not perform tests that demonstrate the digit robot falling when a fall is predicted, but the recovery controller is not activated, as was done in simulation. For all the videos in this section, the detection of the critical fault, and therefore the switch to the recovery controller, will be visualized on the highlighted video with the appearance of a green circle, as you can see on digit right now. It will also be noted on the bottom right of the highlighted video. And the types of faults will also be noted on the bottom left of this video. We start with a critical abrupt fault, and as you will soon see, the algorithm successfully detects the critical abrupt fault and triggers a switch to the recovery controller. We can take a look at that again. It performs similarly for a critical incipient fault. There we go. And now for an intermittent fault, we test the algorithm's performance on a critical intermittent fault that's comprised of 3 faults: an incipient fault, an abrupt fault, which is then lastly followed by an incipient fault. And again, the algorithm successfully detects this critical intermittent fault and triggers the switch to the recovery controller. So now for the abrupt fault, and next for the incipient fault. And now we trigger the switch. Given the algorithm's successful performance on all 3 critical faults, we decided to test the performance of the algorithm on angled pushes, or faults that are introduced from angled pushes. Note that the algorithm was only trained on faults that were introduced by non-angled torso pushes. But despite this, the algorithm is still able to successfully detect the critical angled incipient push, as you will see here. Now it triggered the change. It performs similarly well for a critical abrupt fault that's introduced by an angled push. Next, given the algorithm's successful performance on all of these previous tests, we decided to test its performance on an intermittent fault that's comprised of angled and non-angled pushes. And as you will see, it still successfully detects this critical fault. And now for the angled pushes. And lastly, this is where it will detect. There you go. Now, again, given the algorithm's successful performance, we decided to step up the stakes a little bit and test its performance on an intermittent fault introduced from a leg push. Now, I will be honest, I was very, very nervous during this test, as Gokul will attest. But despite this, the algorithm was still successfully able to detect this critical fault. Do it. I was very nervous. I did not want to break the robot again. And there again we go. So it successfully detected that. Now, up until now, we have implemented database fault prediction algorithms for the task of standing for the planar four-link robot as well as digit. However, database algorithms can perform poorly on out-of-distribution data. So we will now investigate the use of a physics-based binary fault prediction algorithm based on the contact interaction matrix. Recall that the contact interaction matrix captures the interaction of the contact wrenches and the motor torques in achieving the contact constraints and control objectives. Similar to the data-based methods, we will start our investigation by solving the planar four-link problem statement. Here, I will present the preliminary results for detecting critical abrupt and incipient faults. The critical abrupt and incipient faults are detected based on a threshold derived from the conditioning number of the contact interaction matrix. And as you can see, the contact interaction-based binary algorithm is able to detect critical abrupt and incipient faults with similar results to the SVM binary classification algorithm that we saw previously. This therefore demonstrates the potential of the physics-based method. Again, this is a result with false negative and false positive rates of 0. In conclusion, this project contributed to the implementation of a reliable fault prediction algorithm for bipedal robots. We introduced a 1D CNN-based fault prediction method that was capable of not only detecting all 3 critical faults, but also estimating lead time for the bipedal robot digit during the task of standing. We also introduced and analyzed physics-based and database methods for predicting faults of a planar four-link robot. Additionally, all the fall prediction algorithms that were introduced in this section achieved sufficient lead time with 0 false positive and negative rates. The future work for this project is as follows: an expansion of the physics-based method to detect all 3 critical faults in full-sized robots such as Digit, and an extension of the 1D CNN-based method to more diverse environmental conditions, as well as dynamic motions. Given that the projects undertaken in this dissertation focused on developing robust controllers and reliable fault predictions separately, and given the fact that a fault-tolerant framework is comprised of various algorithms working together, additional future directions include the integration of the proposed robust controller and fault prediction algorithms, as well as expanding the implementation scope to include other algorithms, such as a high-level planner or a recovery algorithm. In conclusion, the work presented in this dissertation has greatly contributed to the implementation of a fault-tolerant framework for bipedal robots, and as a result, bipedal robots are now one step closer to achieving their full potential and assisting us in the real world. And with that, I'd now like to go into acknowledgements. For this part, I'd like to say that I will be reading a prepared statement, similar to what Dr. Gumbi over here did, in order to keep the tears to a minimal. I'd like to start by saying that my PhD journey itself has been lengthy, challenging, and yet deeply rewarding, as all my friends here can attest, and my advisor as well. And I could not have done it alone. The saying that it takes a village to raise a child could not be truer. And I am truly thankful for each person who has supported and encouraged, as well as believed in me along the way. So thank you all. To Jesse, my advisor, your belief in me, as well as your mentorship and your guidance, have been very pivotal in my academic journey, especially given the fact that I came to your lab with absolutely no knowledge of control theory. So I'm very grateful for your patience, as well as the opportunities you provided for personal and professional growth. I mean, I got to spend like a summer in France, so that was great. To my committee, I would like to thank you all for your willingness to meet with me individually and to share your knowledge. To Kira, thank you so much for your comment on intermittent faults, because otherwise I would not have been able to do this. So thank you for that. To postdoc Mani, where is Mani? Excuse me, to Professor Mani. Thank you so much for taking the time to meet with me to discuss, the database fault prediction methods, as well as to advise me on career paths, despite all the deadlines and traveling you had to do, which was a lot. So thank you, I appreciate that a lot. To Bobby, thank you for having an open door policy, which I don't know if you remember, but I would always pop by your office after meeting with Jesse to seek your expertise. So thank you for that. To Ayanga, who's not here, but I'd like to thank him for his constant guidance, as well as for answering all the numerous frost and dynamic questions that I had. At the beginning, Ayanga was essentially my co-advisor when I started my PhD. To Najmi, thank you so much for always making yourself available, whether it be for office hours or for research discussion. I still remember this one time where I think you had a conference in Australia and you immediately came to office hours after that. So thank you so much for that. Especially thank you for recently taking the time to meet with me and discuss the model-based fault prediction methods. I really appreciate that. I am immensely fortunate to have been a part of a lab with such a collaborative and welcoming environment. I want to thank everyone in the Bipedal lab for their friendship and insightful discussions. I especially want to thank Grant for his constant availability and willingness to help and discuss ideas, as well as for the Digit repository on which my fall prediction stuff was built on top of. So thank you so much, Grant. Wami, thank you for always making sure I never missed out on events, which is always helpful. Gokul, thank you so much for your extraordinary work on the fall prediction project. This project would not have been possible without Gokul. So thank you for that. To the Wondercraft team, I want to express my gratitude for an incredible internship, as well as for warmly welcoming me as part of your team. To Victor, who I collaborated with on the exoskeleton work. Victor, thank you so much for your time and engaging discussions. I mean, the people in the walk-in lab can attest to how many discussions Victor and I had. So thank you so much. I'd also like to thank the NSF Graduate Research Fellowship Program, as well as the Rackham Merit Fellowship for funding me. To everybody on here. So I am grateful to the robotics, College of Engineering, Mechanical Engineering, Electrical Engineering, and the Engineering Teaching Consultant team. I told you this took a village. As well as the advisors of all the various programs that I was involved in during my PhD for their willingness to listen and provide the necessary assistance and guidance. So thank you all. To my family, to my parents, thank you so much for your tireless sacrifices, your unconditional love, as well as your confidence in my abilities. I mean, you know. I want to express deep gratitude to my grandparents, whose encouragement and support were very crucial to my pursuit of a PhD degree. If it wasn't for my grandparents, I would not be here today. So very grateful to them. To my brothers, they're in separate parts of the room.
Little brothers, right?
To my little brothers. I'd like to thank you all for always putting a smile on my face and for cheering me on. So thank you so much. To the Kenyan community, who I know that you are all tuning in right now, and the rest of my family, words cannot express how truly grateful I am for you all. To my friends now, I couldn't find pictures with all my friends. I don't know what's up with that. I want to, a heartfelt thank you to you all. I want to thank you all for always being there for me, for cheering me on, encouraging me, going on numerous adventures, and sharing countless moments of fun and joy. I truly feel blessed to have you all in my life. Apologies, I really could not find pictures. I want to give a special shout out to Maggie for always lending a year. A year. This is where my Kenyan accent comes out, but a year. And to Khabani over here, I want to thank you for being my pillar of strength throughout this journey. It's been a long journey, but thank you. And with that, I'd like to thank you all for your attention. Thank you so much.